Welcome back to our physics tutorial. This is problem number 2 in our series of problems on one-dimensional kinematics. In this video, we will be solving another question on one-dimensional kinematics with constant acceleration. A motorist traveling at a constant 50 meters per second passes a school crossing where the speed limit is 10 meters per second. Just as the motorist passes the school crossing sign, a police officer in a petrol car parked there starts in pursuit with a constant acceleration of 3 meters per second squared. There are 3 parts to this question. First, let us create the reference frame for this question. The positive x direction is taken to be the direction of travel for both the motorist and the police officer. The origin is at the school crossing. At time t equal to 0, the motorist, let's use m to represent the motorist, is traveling at a constant speed of 15 meters per second, but the acceleration is 0. For the police officer, we use P to represent the police officer. It is traveling with a constant acceleration of 3 meters per second, but at this instant, his velocity is 0 meters per second. So this is the situation that we are facing now. The data is given here. So for part A, how much time elapses before the officer passes the motorist? Now at the instant, the police officer finally catches up with the motorist. The x position for both the motorist and the police officer are the same. So here for the motorist, using the kinematics equation, x equal x naught plus v naught t plus half a t squared. At t equal to 0, the initial position of the motorist is 0. He has a constant speed of 15 meters per second throughout the motion, so this is 15, and he has no acceleration. So we end up with just 15t. On the other hand, for the police officer, using the same formula, x equal x naught plus v naught t plus half a t squared. X naught once again is 0, because at time t equal to 0, the police officer was still at the school crossing. And he started from rest, so v naught is 0. But he has a constant acceleration of 3 meters per second squared. So we end up with 3 over 2 t squared. Now, for them to meet again, after the school crossing, alright, this would mean that 15t has to be equal to 3 over 2 t squared. So that 3t squared minus 30t is equal to 0. 3t, t minus 10. So we obtain 2 answers, either t equal to 0 seconds or t equal to 10 seconds. So the time elapsed is equal to t minus t naught. In this case, it is just 10 minus 0 equal to 10 seconds. Now this t equal to 0 second is when they first met at the school crossing. Alright, and this time t equal to 10 seconds is when they met again, when the police officer finally catches up with the motorist. So that's the reason why we selected this time instead of the 0 seconds. For part B, at that time, what is the officer's speed? Using the kinematics formula, V equal V naught plus A T minus T naught. These will give us 0. Okay, because the initial velocity of the police is just 0 at the school crossing. He has a constant acceleration of 3. T at that time is 10 seconds. When they met again, initial time is 0. So we end up with 30 meters per second. How far has each vehicle traveled? We can solve this part C either from the motorist's perspective or from the police officer's perspective. First, from the officer's perspective. Using the formula x minus x naught equal to v naught t plus half a t squared. Alright, so x naught is 0, so this would mean that x is equal to v naught is also 0 for the police officer. Initial velocity is 0 plus half times acceleration of 3. T is 10 squared. So this will give us a position of 150 meters. From the motorist's perspective, using the same formula, x equal to x naught plus v naught t plus half a t squared. Initial position is 0. Initial velocity is 15. Time is 10. There's no acceleration, so we obtain 150 meters again. And this is to be expected because both vehicles have traveled the same distance when they met each other again. So we have solved this question using kinematic equations. We are now going to solve the same question using the graphical methods. First, sketch the VT graph. First, for the motorist, it's very simple. It's just a straight line. For the police officer is constant acceleration starting from rest. So it looks like this. And this is the time t1 when they meet again. And the final speed or the velocity obtained by the police officer when they meet again, we call it v1. v1 refers to the final speed of the police officer. We know that when they meet again, the displacement of the police officer is equal to the displacement delta x of the motorist. And if we were to consider the area under the VT graph for the police officer, this is using integration from time t0 to t1, v dt is equal to 0 to t1 v dt for the motorist. For the case of the police officer, this area will be equal to the area of the triangle under the VT graph for the police officer. So this area is from 0 to T1 B dt for the police. What about for the motorist? This area is actually the area of a rectangle shown here, which I'm going to shade in another color. Let's shade this area in blue, and there's obviously some overlap here. So this area here, the area in blue, is from 0 to T1 VDT for the motorist. Is the area of a rectangle. And so when they meet according to this equation, these two areas have to be the same. The blue area and the red area have to be the same. So first, for the police officer, is actually the area of a triangle. So it's just half V1 times T1. And for the case of the motorist, is the area of a rectangle is 15 T1. Alright, 15 T1. Why is it 15? Because the motorist has a constant speed of 15 meters per second. Alright, so in this case, we can just cancel away the T1. That will leave us with V1 equal to 30 meters per second. Now remember that our objective is to find out what is T1. Alright. Okay, the elapsed time. So to solve for T1, we need another piece of information, and that comes from the slope of the VT graph for the police officer. The slope here is actually the acceleration of the police officer, and we are going to make use of this piece of information to find out what is T1. So from A equals delta V over delta T. So for the police, 3 meters per second square is delta V over delta T. This means that delta V is equal to 3 delta T. So that delta V here is V1 minus 0. Alright, from the graph, delta V is referring to this vertical distance here. So if I may draw this is actually delta V, and delta T is just this length here, delta T. So this is equal to 3 times T1 minus 0, and this will give us T1 equal to V1 over 3, which is equal to 30 over 3, giving us 10 seconds. So the elapsed time is just 10 seconds. Alright. And then for part B, at that time, what is the officer's speed? And this has already been solved here, right? At that time, the officer's speed V1, referring to this point here. At that time T1, the officer's speed is V1, and it is just 30 meters per second. Right, so we solve part A and B at the same time. Finally, for part C, how far has each vehicle traveled? In this case, the distance traveled by both vehicles is the same, so we can solve it either from the officer's perspective or from the motorist's perspective. So, distance traveled by motorist is just the area of the rectangle, and this is given by 15 times T1 equal to 15 times T1 has a value of 10 seconds, giving us 150 meters. Or we can also use the distance traveled by the police officer. They should be the same. Equal to the area of the triangle, half V1 T1, which is half times 30 times 10, giving us once again 150 meters. Okay, we have solved the entire question using both kinematic equations and graphical method using the VT graph. I hope you enjoyed today's video, and I will see you again in our next video.